This is the homework for page 209, reviewing the extreme value theorem. So before we begin doing the work, let's just remind ourselves of what the extreme value theorem says. The extreme value theorem is an existence theorem, which means it simply promises that an extreme value will exist if the conditions are met. So the conditions of the extreme value theorem are: we must have a function that is continuous, no breaks, gaps, or holes, on a closed interval. So the closed interval might be from a to b, meaning that the function is continuous at a and the function is continuous at b. If that condition holds true, then there will be, for sure, the promise is an absolute max on the interval and an absolute min on the interval. And the candidates that we will test are the endpoints. So if there is an extreme y value and an absolute maximum and an absolute minimum, they will occur at the endpoints or they will occur at critical numbers. And from your lesson in class or the video, you know that an extreme value is where the first derivative is either 0 or don't forget about the situation where the first derivative is undefined. And we will see that in this homework. So in number 1, let me bring the directions down. In number 1, decide whether each labeled point is an absolute maximum, an absolute minimum, a relative maximum, a relative minimum, or none of these. And the word relative could be replaced with local. So we talked about that in class as well. A relative max, a local max. So when we we start by looking at the point at A, and that is not the lowest y value of the graph, and it's certainly not a local minimum because it's not a turning point. So A would be none. B, the graph changes from increasing to decreasing. So at B, we see two things. B is the highest y value of the entire graph, so this is the absolute max. And it is also, in this little neighborhood right here, it is a local or a relative max. At C, we notice the graph continues to move downward, so there's no change. It's a decrease to decrease. So at C, there is not an absolute max or min, nor a local max or min, so that would be none. At D, we see the graph is not continuous, so there can be nothing going on there, no local or absolute anything. At letter E, the graph changes from increasing to decreasing, so it's not the highest y value of the graph, but in that little neighborhood, it is a local or a relative max. At letter F, the graph changes from decreasing to increasing. It is not the lowest y value of the graph, so it's not the absolute minimum, but in that little neighborhood, it is a local or a relative minimum. And at letter G, that's not the highest y value, and it's not a turning point, so G is none. It's not the local, it's not the absolute. Moving on to the second graph, letter A is clearly the lowest y value of the graph, so it is the absolute minimum point, or y value, because the absolute minimum is a y value. Absolute max, all these are y values. They occur at x values, but what they are y values. At B, the graph changes from increasing to decreasing, so it's not the highest y value of the graph, so it's not absolute max, but it is in that little neighborhood. It's a local or a relative max. At letter C, the graph continues to go from decrease to decrease, so there's no change, so that's not a local or absolute anything. At letter D, the graph changes from decrease to increase, so we're looking at, it's not the lowest y value of the graph. We've already established that at A, so it is a local or a relative minimum in that little neighborhood. When we get to E, the graph changes from increase to decrease, not the highest y value of the graph, but in that neighborhood, it is a local or a relative minimum. Just throwing both of those words so we get familiar. And that was letter F. And when we get to letter G, we see a discontinuity, so nothing is happening there, not absolute, local, anything. All right, let's go on and let's actually practice the extreme value theorem in exercises 21 to 38, and I believe we're doing 21 to 35 every other odd. So since we're doing every other odd, 21, skip 23, go to 25, 29, and did I circle those right? 23 to 35 every other odd. So let's get rid of that. Come on, eraser. There we go. Glad I reread that. I didn't want to do the wrong problems. So 23, 27, 31, and 35. So those are the problems that we're going to take a look at. And we're looking for the absolute max and the absolute minimum if they exist. So first, we're always going to check to see if the conditions of the theorem are met. So in number 23, which I'll do right here, we have f of x equal to negative x squared plus 3x. We know that negative x squared plus 3x is a parabola that opens downward, and we know that that function's continuous everywhere. So it's certainly continuous on the closed interval from 0 to 3. So since f of x is continuous on the closed interval from 0 to 3, f of x has an absolute max and an absolute min by the extreme value theorem. So you want to get used to being able to write those up, write that statement up to justify your reasoning. Excuse me. All right, so let's figure out who our candidates are, to where the absolute max and where the absolute. So this is the where, not the what. So the candidates, the endpoints. And the endpoints for us, I'm going to go ahead and create a table of values because that's how we're going to make our decision. So x and f of x. Remember, when you're checking the y values, you go back to the original. So we have an endpoint at 0 and we have an endpoint at 3, and I'm going to just leave some space for any critical numbers that we find. The other candidates are any critical numbers that we find, and that is where the first derivative is equal to 0 or undefined. So I'm going to find the first derivative of my function. So f prime of x using the power rule is negative 2x plus 3. I'm going to set that equal to 0 to figure out where any critical numbers are. Subtract 3, divide by negative 2, and we get 3 over 2. So we have a critical number of 3/2, which is between 0 and 3. And so now I'm going to substitute each of those into f. So I'm going to find, I'll go back up here, I'm going to find f of 0, f of 3/2, and f of 3 to compare the y values. So I can see that if I substitute 0 in for x, I get a y value of, oh, see, I already did exactly what I told you guys to be careful of. Go back to the original. So right here, if I substitute 0 in for f, I get the opposite of 0 squared plus 3 times 0, which will give me 0. So the y value there is 0. If I substitute 3 over 2, I get the opposite of 3/2. That's squared plus 3 times 3/2. When I square that, I get 9/4 plus, here I'm going to get 9/2, which is the same thing as 18 over 4. which gives me a y value of 9/4. So the y value here is 9/4. And when I substitute 3, so f of 3 is equal to the opposite of 3 squared plus 3 times 3, which is negative 9 plus 9, which is 0. So the absolute minimum is 0. So the absolute min is 0, and the absolute max is 9/4. Now, if you want to talk about the x values, because sometimes the problem might say, where does the absolute maximum occur? We would say the absolute minimum occurs at x equal to 0 and 3, and is 0. So in other words, notice there's only one absolute minimum and one absolute maximum. The absolute minimum and the absolute maximum may occur more than one time, but there's only one high y and one lowest y. Okay, so let's get rid of that. That's going to also clear my numbers, so hopefully I don't get myself confused here. All right, let's clear the annotations, and let's go to number 27. Okay, give that a second. All right, 27. In number 27, we have y equal to 3x to the 2/3 power minus 2x on the closed interval from -1 to 2. Now, if you think about x to the 2/3 power, I'm going to come over here to the left-hand side. X to the 2/3 power is the same thing as the cube root of x quantity squared, which is the same thing as the cube root of x squared, however you want to look at it. But the reason I'm talking about this is we can take the cube root of any number, positive, negative, fractions, decimals, 0, and it's all good. And then we square it, we output a positive. The reason I'm thinking about that is when I come back over here to my function, I want to remember this term is by itself, 3x to the 2/3 would be a continuous graph. 2x is linear, so that would be continuous. So since y is continuous, it's everywhere, but continuous on specifically the closed interval from -1 to 2, y has an absolute max and absolute min. I'm not going to write this up every time. I probably won't do it after this, but I'm just modeling for you how to write it up. By the extreme value theorem. Okay. Now we're going to need our candidates. Where might this happen? So the candidates, as we talked about, are endpoints and critical numbers. The endpoints are -1 and 2. Those are values of x. And the critical numbers is where the first derivative is 0. Don't forget the or undefined. So I'm going to find my first derivative using the power rule. So y prime is equal to, when I do the power rule, 3 times 2/3 is 2x, decrease the power by 1 to the -1/3 power, minus 2. To find critical numbers, I'm going to set that equal to 0. Now notice I'm also going to move the x to the -1/3 power to the denominator and make it into a radical, since I'm going to have to do algebra to this. So that's the cube root of x minus 2 set equal to 0. Now notice when I move that to the denominator, I see that there is a value of x that would make this derivative go undefined. So right here, if x were 0, that derivative would go undefined, and that's what I was talking about. So we have a critical number of 0, and notice I identified that by not doing any algebra, but by realizing there was a variable in the denominator. All right, now by solving, I'm going to see if I have any other critical numbers. So I'm going to add 2 to the right-hand side. So I have 2 over the cube root of x is equal to 2, and I can put that over 1. To solve, I'm going to cross multiply, so I get 2 equal to 2 cube root of x. Divide both sides by 2, and I get 1 equal to the cube root of x. Cube both sides, and x is equal to 1. Okay, so I'm going to create my table of values because I need to compare the y values. I know where the absolute max and min might occur, but I need to know what they are. So my endpoints are -1 and 2. My critical numbers are 0 and 1. So remember, I'm going to substitute those into original y. So y of -1, that'll give me 3 times -1 to the 2/3 power minus 2 times -1. Now remember, back over here on the left-hand side, we said that that is the cube root of the number squared. So the cube root of -1 is -1, squared is +1, times 3 is 3. -2 times -1 is +2, and 3 plus 2 is 5. Y of 0 would be, if I substitute 0, I'll get 0 plus 0, which is 0. Substituting 1 gives me 3 times 1 to the 2/3 power minus 2 times 1. So 1 to that power is 1 times 3 is 3. -2 times 1 is -2, and 3 minus 2 is 1. And then substituting 2, I get 3 to the times 2 to the 2/3 power minus 2 times 2. So I'm just noticing now that when I copied this problem, I used the wrong closed interval. I picked up number 25. Our closed interval is at 1. So yeah, I was kind of worried about 2 to the 2/3 power without a calculator. All right, so 2 is not one of the candidates because it's not an endpoint. So here I have a critical number that also happens to be an endpoint, and it doesn't matter, it's still one of the candidates either way. So from the data in the table, I can see that the absolute max is 5, and it occurs at -1. The absolute min is 0, and it occurs at 0. All right, moving on, we did 27, so now we're going to do 31. So let me clear the screen and restart that. Okay, and I'm going to bring this down a little bit. 31. In number 31, we have h of s equal to, notice I'm going to bring that denominator to the numerator and make it to the -1 power for easier differentiation. But before I do, I need to think about h of s is equal to 1 over s minus 2. Now we know this is a rational function, and if s is equal to 2, we know that there's going to be a vertical asymptote, which is a discontinuity, which means that the graph overall, 1 over s minus 2, is not a continuous function. So let me look at the closed interval. Now I'll make sure I copy it correctly. The closed interval is from 0 to 1. Good news, 2 is not on the closed interval from 0 to 1. So this function is continuous on the closed interval. So h of s is continuous on the closed interval from 0 to 1. So h of s has an absolute max and an absolute min by the extreme value theorem. Okay, let's find our candidates. Our candidates are the endpoints, and any critical numbers. So endpoints in this case are 0 and 1. I think I copied those down this time correctly. Critical numbers are any values of x where f prime of, or h in this case, where h prime of s is equal to 0 or h prime of s is undefined. And the undefined is the one that we want to tend to forget about. H prime of s using the chain rule would be -1 times s minus 2 to the -2. The derivative of s with respect to s is 1. So I'm going to rewrite that to make h prime of x equal to -1 over s minus 2 quantity squared. And now that I have a fraction and I have a variable in the denominator, I can see that if s is equal to 2, then h prime of s is undefined, so 2 is a critical number. However, we already know that 2 is not on the closed interval, so even though it's a critical number, we're not going to consider it because we're only consider what's happening on the closed interval. So far we have s and we have h of s. We have 0 as an endpoint and 1 as an endpoint. All right, so now I'm going to set the first derivative equal to 0, so -1 over s minus 2 quantity squared equal to 0. Our derivative is a fraction with a numerator and a denominator. And the only way a fraction can equal to 0 is if the numerator is equal to 0. However, in this case, our numerator is set at -1. It doesn't have a variable in it, so this fraction can never equal to 0. So what happens, I just don't get any critical numbers. So the only two places that I'm going to test out for the absolute max and min are the two endpoints. All right, so let's substitute and see what we get. So h of 0, go back to the original function, so back over here was my original. If I substitute 0 in place of s, I'll get -1/2. If I substitute 1 in place of s, I'll get 1 over -1, which is -1. So the absolute max occurs at 0 and is -1/2, and the absolute minimum, lowest y value, occurs at x equal to 1 and is -1. All right, that's 31, and let's go on to 35. So let's clear the screen. And we have a trig function, cosine of pi x. Screen's going to clear here any second now. Let's try that again. Clear annotations. All right, so if we think about y equal to, or in this case f of x equal to cosine of pi x, closed interval from 0 to 1/6. Cosine of pi x, or the cosine function, is a continuous function. It has no breaks, gaps, or holes. So f of x is continuous everywhere, and it's certainly continuous closed interval on the closed interval from 0 to 1/6. I'm not going to write that up again because I've written it up for you several times. So the candidates are the endpoints and the critical numbers. The endpoints are 0 and 1/6. Critical numbers are where the first derivative is 0 or undefined. So let's get our first derivative. So f prime of x, the derivative of cosine is negative sine of the angle, pi x. Remember, there's understood parentheses around the angle. Don't forget to take the derivative of the angle by the chain rule, ladies and gentlemen. The derivative of pi x is pi. So our simplified first derivative is negative pi sine pi x. And so I'm going to set that equal to 0 to find any critical numbers. There's not a place where this derivative is going to go undefined. Solving that, I'm going to divide both sides by negative pi, and I get sine of pi x still equal to 0. And this really says the sine of some angle, and the angle happens to be pi x, is equal to 0. And we're only going to consider on the interval from 0, which starts right here, to 1/6. Now pi over 2 is up here, which is 1.571. So 0 to 1/6 is not very far of a move. It's definitely in the first quadrant. And so on this closed interval from 0 to 1/6, the only place that the y value, the sine, is equal to 0 is at 0. So my angle has to equal to 0, which means my angle is pi x. So x equals 0. All right, so I don't pick up any critical numbers again. So because 0 is already one of the endpoints, so I'm going to make a table of values. And it's okay if you don't get additional critical numbers. It just means that the highest y value and the lowest y value will occur at the endpoint. So I have x, and I have f of x, and I have 0, and I have 1/6. Remember, into the original. So I'm substituting 0 into cosine of pi times 0, which is the cosine of 0, which is 1. And then when I substitute 1/6, I have the cosine of pi times 1/6 is pi over 6, which is 30 degrees. And the cosine of 30 degrees is root 3 over 2. And 1 is greater than root 3 over 2, so the absolute max occurs at x equals 0 and is 1. The absolute min occurs at 1/6 and is root 3 over 2. And so finally, let's take a look at the last two problems. In these two problems, they are asking us to sketch a graph given certain conditions. And when we move this up, we'll see that they're looking for not the graph. It's important to understand not the graph. There's not necessarily just one graph. We're looking for a function, so it has to pass the vertical line test, with the given characteristics, and we're only going to go from -2 to 5. So for number 61, I'm going to begin my graph by just putting the -2 and 5 on there so I know where we're starting and stopping. So there's -2, 1, 2, 3, 4, 5. All right, 61. I have the highest y value, the absolute maximum is occurring at -2. The lowest y value of the graph will occur at x equal to 1, so I'm going to put a 1 on there. The relative maximum, remember a relative maximum is just a turning point, occurs at x equal to 3. So I have 1, 2, 3 different criteria. All right, so this is what I have to make happen at x equal to 3. And y value is occurring at -2, so I'm just going to randomly stick it up here. My absolute minimum occurs at x equal to 1, so it just has to be like maybe, I don't know, way down here somewhere. I'm just randomly sticking it, and the graph might travel like that. It might be linear. I don't know. I'm just making something up just to meet the criteria. Right now at x equal to 3, I have to create a little local maximum, but it can't go higher than 2 because 2 had to be the absolute maximum. So I'm just going to make a little turning point there. And then I'm going to go over here to 5 and make it do something like that. I don't want it to go lower than x equal to 1. So I have here the absolute max, which is what they told me to do. I have the absolute minimum. I have a relative max. And at 5, it doesn't really matter. I just had to make those 3 criteria occur. Not the only graph, not the only way that it can look. It could have discontinuities. Didn't say that it couldn't have a discontinuity, but it had to be a function. So my graph does pass the vertical line test, and it had to have all 3 criteria. All right, let's do the last one. And in number 62, we have a graph, and it's going to be on the same interval from -2, 1, 2. There's -2, 1, 2, 3, 4, 5. There's 5. And this time we have a relative minimum at -1, so that's a turning point that looks like that. At x equal to 0, we have a critical number but no extrema. Now, in order to make a critical number, in other words, the first derivative 0, we want to make something that looks like our friend x cubed, so something, whoops, yeah, that's kind of exaggerated, something like that, or something like that, because at that point right there, the slope does go to 0. I want the highest y value at x equal to 2 and the lowest y value at x equal to 5. All right, so at x equal to 5, maybe I'll be like, okay, we're going to be way down here. We want to do something at -1, so I'm going to put that on my graph at 0 and at absolute maximum at x equal to +2. All right, so at -1, I have to have a local minimum, so I'm just going to start my graph randomly. There's a random choice here. Make a local minimum there. Now, when I come up, I'm going to try to create this little cubic feature, point of inflection. So if that's cubic, that would be something like flatten out at 0 and make a turn like that. High y value at 2, and then low y value at 5. So I have a relative minimum, which is what I needed. I have the absolute maximum at 2, which is what I wanted. I have critical number, but not local max or local min at 0. It's not the greatest graph drawing of that cubic feature, and then the absolute minimum occurs at x equal to 5. So there's your homework on 209.